Let us take a look at the spectrochemical series. Spectrochemical series is a list of ligands arranged based on the strength of the metal-ligand interaction. That is the type of interactions happening in coordination complexes. Now, the strength of the ligand decides the splitting energy, the type of complex formed, that is whether it will be a high spin complex or a low spin complex, and as a result whether it will be diamagnetic or paramagnetic, then the color of the complex. All these things are dependent on the strength of the ligand. The crystal field splitting energy is also dependent on the strength of the ligand. So these are the ligands which we often come across. This is iodide, bromide, sulfide, thiocyanide, chloride, nitro, then fluoride. Here this is NO2, but the connection or the bonding is through oxygen here. Then OH minus, C2O42 minus, that is oxalate, O2 minus, then water. Then we have, towards the right of water, we have a set of ligands. That is the isocyanide, EDTA, ethylene diamine tetraacetate, then ammonia, ethylene diamine, then NO2. Here remember that nitrogen is the donor. Then cyanide, carbonyl, etc. There are a lot more other ligands which you have learned. Now in this series we can say that the ligands towards the left of water are weak field ligands, and the ligands to the right side of water are strong field ligands. So if you know this series by heart, it is quite easy for you to, for some people it is easy, for some it is not so easy. So if it is not easy for you to learn all this by heart, you can use a trick. That is, when you see a ligand, try to find the donor atoms in that ligand. If the donor atoms are halogens like fluoride, chloride, bromide, iodide, oxygen or sulfur, like in these OH minus, S2 minus, SCN minus, NO2 minus, C2O42 minus, etc. You can see oxygen or sulfur are the electron donors, or they are the ones who are donating the electron pairs, and here it is the halogens. If halogens, oxygen or sulfur are the electron donors, then they come under the category of weak field ligands. Whereas if the donor atoms are carbon, nitrogen or phosphorus, then those ligands will act as strong field ligands, like in Cn minus, Nc minus, CO minus, NH3 minus, En, EDTA4 minus, PPH3, etc. The donors you have to identify. Here in Cn minus it is carbon, in Nc minus it is nitrogen, in CO minus it is again carbon, NH3 it is N, En it is N, nitrogen, EDTA again it is nitrogen, and PPH3 it is phosphorus. So if carbon, nitrogen or phosphorus act as the donor atoms, then they will be strong field ligands. Now in that series we saw that water is given a special place. Now water behaves a little differently. Water acts as a strong ligand or strong field ligand with cobalt, nickel and copper in their +3 oxidation states. Remember, with cobalt, nickel and copper in their +3 oxidation states, water acts as a strong field ligand. And water acts as a weak field ligand for scandium, titanium, vanadium, chromium, manganese and iron in their +3 oxidation states. So remember this. Donor atoms, if the donor atoms in a ligand are fluoride and the halogens, oxygen or sulfur, then they belong to weak field ligand category. And if the donor atoms of the ligands are carbon, nitrogen or phosphorus, then they act as strong field ligand category. And water will be a strong field ligand with cobalt, nickel and copper in their +3 oxidation states, and acts as a weak field ligand for scandium, titanium, vanadium, chromium, manganese and iron in their +3 oxidation states.